Yeah, it has not come in the live view yet. Okay. Because I need to mute that light screen now when it starts. Yeah, now it appears, so then I will mute it. Good evening. Course on chemical crystallography. Hope you are able to follow the lectures and you are able to answer the assignment questions that we have already gone through. And I have answered some questions over email that I have received in the past 3 to 4 weeks. And there are some questions from 4th week and 5th week lectures, and those who want to ask questions now can post your question in the chat box. So I will address those in the due course. So let us quickly start with the questions that I have received through email. The first question that I got is why the detector was placed at a 2 theta angle in the diffractometer, why not theta? So to understand this, we need to go back to our understanding of Bragg's law and how the diffraction occurs. So when we try to think of two planes in the crystal and the X-rays fall on one plane, this is the incident radiation and that is the diffracted radiation. And if we draw a perpendicular, the angle here is theta. So as a result, this angle is also theta and this angle is theta. So if you did not have the crystal, the beam would have directly passed in this direction. Because of the plane that is diffracting the X-rays, it is diffracted in a direction which is shown here. So the angle at which the incident radiation is diverted or deviated is not only theta, it is theta plus theta. So that is why this angle is your 2 theta. So whenever we try to represent the powder X-ray diffraction pattern, which I think the question has originated from, so in case of a powder X-ray diffractogram, what we plot are the arbitrary intensity of the diffracted beam in y-axis, and we plot the angle 2 theta instead of theta in the x-axis, and then we get the diffracted beam and diffracted intensities like that, as you have seen in my lecture. And this intensity dies down with higher angle of 2 theta. So this representation 2 theta originates from the theory of diffraction, where it is the angle at which the incident ray is diffracted. The incident ray, the direction of that incident ray is changed. So that angle is 2 theta, and that is why we always represent X-ray diffraction in terms of 2 theta. So when we talk about single crystal X-ray diffraction, there also we talk about should collect the data up to 2 theta 50 degree or 100 degree. That one has to decide based on what kind of experiment you are trying to do. Hope this clarifies the first term. There is a query regarding 2 questions, question number 3 and 4 in assignment 5. So in the assignment 5, question number 3 was, what is the volume of reciprocal lattice in monoclinic system? See, the volume of monoclinic unit cell is ABC sin beta, and we write volume as ABC sin beta, and volume of reciprocal lattice, that is V star, is 1 by V, that is 1 by ABC sine beta. And then, in terms of reciprocal unit cell dimensions, this 1 by A is nothing but A star sine beta star. This 1 by C means C star sine beta star, and B remains, B becomes, that 1 by B is nothing but B star, and we still have sine beta. So now, as you know, sine 180 minus beta is nothing but sine beta, and this 180 minus beta is actually beta star. So instead of sine beta, I can write sine beta star. So A star sine beta star into C star sine beta star into B star divided by sine beta star. Because if I write sine beta, which is equivalent to sine 180 minus beta, and sine 180 minus beta is nothing but sine beta star. So now we cancel sine beta star with sine beta star. So what we get as the volume of the reciprocal lattice is A star, B star, C star, sine beta star. So it is the option C which is the correct option. And in case of question number 4, let us erase this. In case of question number 4, which reflection is present in reciprocal lattice for a F-centered lattice? So, a face-centered lattice, what kind of reflection should be present? So, what are the systematic absence conditions for a face-centered lattice? For a face-centered lattice, for general set of HKL reflections, H plus K equal to 2n plus 1 will be absent. For A-centered lattice, similarly, K plus L equal to 2n plus 1 should be absent, and H plus L equal to 2n plus 1 should be absent. What does it mean? It means that the reflections where all the three conditions are simultaneously met, those reflections will be absent. So in this particular case, I think there is a typo error. The question should be which reflection is absent in the reciprocal lattice, not present, and that is where probably you have the confusion. So we will rectify this when we do the evaluation of question 4. So it should be 201, which should be absent, because this 2 plus 0 is even, plus 2 plus 1 is odd, 1 plus 0 is odd. So this reflection does not meet all that criteria, so it should be present. Sorry, it should be absent. So that means here the sum is even, this sum is odd, and that sum is odd. So not all the three sums are odd. So this reflection is systematically absent. So then what is present? All even and all odd reflections are the reflections which are present. Okay? Then the third question that I have here is spinels are whether the spinels are following the radius ratio or not. Is magnesium 2 plus greater than aluminium 3 plus in size? So magnesium 2 plus goes to tetrahedral site and aluminium 3 plus goes to octahedral site. Why not all tetrahedral sites are filled and all octahedral sites are not filled? Good question. See, what will happen is that the radius ratio is certainly followed and the size of the octahedral and tetrahedral sites are different. So when you have such difference, preferentially smaller ion will go to a smaller site, larger ion will go to a larger site. And of course, one has to keep in mind what the chemical formula is for the charge balance purpose. So when you have to manage a charge balance, you have to have a stable structure. So you have to fill the vacant sites, the tetrahedral or octahedral sites in such a way that you achieve a closed packed geometry and you do not create any imbalance. So the smaller ions will go to a smaller site like the tetrahedral holes, larger ions will go to a larger site like the octahedral holes, and it will alternately occupy tetrahedral and octahedral holes so that the vacant sites are uniformly filled inside the lattice to bring stability to the structure. It cannot happen that all of them will go to tetrahedral site or all of them will go to octahedral site and leaving the other site completely empty. So that structure will not be a stable structure, and that is why we do not, we have alternate tetrahedral and octahedral sites are vacant and empty. Then we have a question, why we have to take 1/4 shift of origin? Is it shifted? If shifted or not shifted, the transform matrix will vary. No, the transformation matrix will not vary. And the concept of 1/4 comes from where? Now let us take one example. Suppose I have a two-dimensional coordinate system where this is x and that is y. Sorry, this is x in the positive direction and this is the negative direction. That is positive direction of y and this is negative direction of y. And in the space, I have 2 points, x1, y1, and somewhere here, x2, y2. And I join them to a straight line like this. These 2 points may have 2 coordinates which are centrosymmetrically related, but there is a translational component associated with it. So if I consider the coordinate with respect to this origin located at the center, then the coordinates of x1 and y1 could be such that the center of inversion relationship is not visible. There will be a translational component associated with it. So instead of having the center of inversion here, the midpoint of these two here, if we have the midpoint somewhere here and we draw our coordinate system like this, considering the origin is shifted there, from this point, the coordinate of that will be x2 prime, y2 prime, and the coordinate of that will be x1 prime, y1 prime. And these 2 points, which are written in blue, will be centrosymmetrically related. So in our case, where we have to do this origin shifting, that is in case of P21 by C space group or P21 by N space group, you will see that you have a point which is x, y, z, and you will see that there is a point which is In case of P21 by C, it is half minus x. I think it is half minus y and z. Sorry, minus z. So here you see the relationship is inverse. The relationship is like inversion center. X is going to x bar, y bar, z bar, but there is a component half which is associated with it. So that means the 2 points which we are talking about are identified by two quantities, x, y, z, and half minus x, half minus y, and minus z with respect to an origin which is probably somewhere here. So now instead of this origin, if we shift the origin to some other place, then we will have a new set of coordinates which will be x, y, z and x bar, y bar, z bar. So these two coordinates will then be centrosymmetrically related with respect to the new point. So this new point should be shifted from here by what extent? By the extent of 1/4 along x and 1/4 along y. So that here we reduce 1/4, here we increase 1/4. So like that, the concept of 1/4 appears in case of origin shifting. So whenever you see the shifting of origin, you will see there is a translational component 1/4 either along x, y, or x and z, or only along z, depending on which system you are actually talking about. This you may visualize in case of the space group P212121, where you may have noticed that the 3-2-1 screw axis that we considered, if we consider 1-2-1 screw axis in the plane of the board like that, then we consider a second 2-1 screw which is 1/4 shifted from the plane of the board somewhere here. This is 1/4 shifted from the plane of the board, and the third 2-1 that we have is both 1/4 shifted from this and 1/4 shifted from that. So it goes to a point which is here. So if you look at the stereographic projection for P212121 in the textbook or in the website that I have shared, then probably you will be able to understand. Let me try to look at, I should be able to share a screen here. So I should be able to show you how the 212121 space group looks like. Just give me a second. So let me share my screen here so that you can have a look at you can look at the P212121 space group. See here, what we have is this projection is made with B axis in the vertical direction, A axis here. So the 2-1 which is parallel to A is shifted 1/4 along B, which you can see here. The 2-1 screw, which is parallel to B, is actually 1/4 shifted from the plane of projection. So these two are non-intersecting. And the third 2-1, which is further shifted along 1/4 along X and 1/4 along Y. Sorry, 1/4 along X. So this one is here. So this is a third 2-1. So 1 2-1 is like that. The other 2-1 is like this. And a third 2-1 goes like that. Hope you can understand the importance of 1/4 shift in case of 2-1 screw, or even in case of 2-1 by C kind of a space. So then I can go back to some questions which we have recently received in the Google form. The first question is, what are the job opportunities that one can get in the field of chemical crystallography in both research and industry? And what are the prerequisites or qualifications one must have for it? See, the subject crystallography is always used everywhere in structure determination. So in academic organizations, the people who are working in synthetic, organic, inorganic, organometallic chemistry labs, or even solid state chemistry laboratories, they have to determine the structure. So those who are doing PhD or masters in chemistry related areas would need this course very efficient, very effectively they will need it. And in the industry, in pharma industry or in any other industry where material science research is conducted, there may be structural chemistry, structural study of the materials that they make is required. So in pharma industry, we can find application for X-ray crystallography. Every pharma industry requires powder X-ray diffraction facility and, if possible, single crystal, because they cannot establish the structure of their drug without a crystal structure of the drug. And to be able to work in those industry as a crystallography person, one at least must have master's degree with chemistry and a knowledge of crystallography. And those who have done PhD in chemistry with crystallography as one of the subjects studied in the PhD, or maybe worked in the crystallography lab for PhD, would get a job in industry as a crystallographer. And also, of course, like me, one can work in academic institute and work on crystallography related projects. Hope that clears your doubt. Then there are three questions from one person. Why we need to introduce reciprocal lattice and what is its significance? So let us first talk about that. See, the concept of reciprocal lattice I have discussed in the lecture, that it is introduced to understand the theory of diffraction better. The concept of X-ray diffraction comes from the planes, that the planes of atoms which are present in the unit cell, and they are diffracted. But then when you try to imagine a crystal which is extremely small, you try to identify different planes in a tiny crystal, it is not physically visualizable which plane is oriented in which direction, and it is not possible to understand how one should orient the crystal so that one particular plane will come into a diffraction condition. So that is why we considered the reciprocal lattice concept, which are tried to convert each and every crystallographic plane to an imaginary point. And we saw that those imaginary points fall in some kind of sphere called the Ewald sphere. And a sphere of radius 1 by lambda is the sphere which contains a certain number of reciprocal lattice points, which meets the Bragg condition when it crosses the circumference of the sphere. So at that point, one can identify what radiation to use to achieve what kind of resolution and so on, because it is now directly related to the wavelength. So the radius of 2 by lambda, that the sphere of radius 2 by lambda contains a certain number of reciprocal lattice points, which actually originates from a certain number of crystallographic planes. The reflections that fall within that sphere of radius 2 by lambda can be achieved during the diffraction. So to understand how and how many number of planes can meet the diffraction condition with a given wavelength, one has to consider the reciprocal lattice. Okay, so the next question that I can see here, what is the relationship between resolution and D values? This can be explained in a simple way. Suppose if I want to know what is there inside this box, I have a box in front of me and I want to know what is there inside the box and I don't know how to see. What are you going to do? We would like to make slices of this box and try to then see what all are there inside the box. Suppose if you have a piece of bread, a large piece of loaf, and that is not sliced. So you don't know whether it has kaju kismis inside, or it has some fruits, or it has nothing. So what we try to do is we try to cut the bread in multiple slices and then try to understand what is inside. So now finer is your cut, your understanding is more finer about the internal structure of that particular piece of bread. So here also, in case of crystal structure, what we try to do is we try to see how small d values can be observed. So the diffraction from small d values need to be understood, need to be identified to get the actual picture inside the unit cell. So a resolution means how well you can see the inner material of that particular crystal. So if you have a crystal and for that you know the d value only up to 50 degrees in 2 theta, you know a certain amount. If you get the data up to 100 degree in 2 theta, which means a much smaller d value, that means you know much finer information about that crystal. So using a routine data, you can only solve the structure of the atom. You can find out which atom is where, carbon, nitrogen, hydrogen, oxygen, fluorine and other metals. But you cannot visualize the intermolecular electron density. Suppose one molecule is here and another molecule is here. How is the electron density distributed between the two molecules, which may be bonded by hydrogen bond, which may be bonded by van der Waals interactions, which may be bonded by some other interactions like including CHF interactions or halogen-halogen interactions. So how those molecules are interacting in space, if you want to know, you need to get a high resolution data. That means you need to slice the unit cell in finer slices. That means you need to go to a very close d values, the planes which are very closely spaced. And that is why higher the resolution, lower is the d value. Okay, so there is a question from the same person. Explain the stereographic projections of 3 bar M and 3M. So what is 3 bar? 3 bar means threefold rotation followed by inversion. So if I want to do the projection here, first of all, I should divide it into 6 parts, or rather with 3 lines which are 120 degree apart. So now when I'm trying to do 3 bar, let us start with this point. I should do 120-degree rotation. So 60-degree plus 60-degree rotation and inversion. So when I invert, the open circle becomes, the closed circle becomes the open circle. Then again we do 120-degree rotation, 60 plus 60, and inversion comes here. Then again 120-degree rotation and inversion brings it here. 120-degree rotation and inversion brings it there. Whenever I am inverting, it changes from open circle to closed circle or closed circle to open circle. So from here to there it goes 120 and inversion makes it here. 120-degree rotation and inversion it brings it here. So now I have made 3 bar. So this is now 3 bar. And now if I draw M, I should draw M along this. So this line corresponds to my mirror. So whatever objects are on the right should have the same thing on the left. If it is here, it goes there. If it is here, it goes there. If it is here, it goes there. If it is here, that goes there. See, by default, what has happened is this mirror is generated and that mirror is also generated. So this is 3 bar M. Is that clear? So technically, these 3 are mirror planes which are parallel to your 3 bar axis and passing through one point. So all the 3 planes are intersecting planes. Now when we go for 3M, how should it look like? So again the same thing, I should divide it into 6 parts by drawing 3 lines at 120-degree angle because this is a 3-fold axis. Right? So now I should do 3 with a point. So 120-degree rotation brings it here. Another 120-degree rotation brings it here. So this is nothing but 3. And when I say M, the mirror is here. So if I just apply this mirror, what happens? This point is projected here. This point is projected there. This point is projected there. So which essentially means the lines which I had drawn are now serving as the purpose of a mirror. So now can you see the difference between 3 bar M and 3M? Correct? Is it clear to the person who asked the question? I hope the person is available online. Then there is another question. Okay, so there is no further question in the Google form. Now let me check the questions that I have received here. No, the option A, Manish Sharma has asked option A, what is the volume of reciprocal lattice in monoclinic system? So reciprocal lattice should have a volume of, in the term of reciprocal lattice parameter. So that should be A star, B star, C star, sin beta star. The first option A is ABC sine beta, which is the volume of the direct lattice, which means the first option will have unit in cubic angstrom, and third option C will have unit in cubic angstrom inverse, 1 by angstrom, 1 by angstrom cube. Okay? So is there any other question that I should answer? In the Google Prof form, there are only 4 questions. Okay, if there are no more questions, I can discuss one thing which probably you may have problem in understanding, but you have not asked. Somebody may have a problem in understanding the space group representations for a tetragonal system, which actually we have not discussed much in the class. So, in case of tetragonal system, you know the space, the fourfold axis is parallel to C. So that we always should remember. And with that, we should try to understand 2 space groups, I4 and I41. These are the 2 space groups I would like to draw here and explain how these are drawn. And I will draw these 2 space groups using the letter F, assuming that the letter F is my object. So when you are trying to draw a tetragonal unit cell, the projection of a tetragonal unit cell, we always should draw a square. And the fourfold axis that is there is always perpendicular to the plane of projection. So this direction is B and that direction is A, which we should always maintain. So when I say 4, that fourfold axis is perpendicular to the plane of the board, and that projection is drawn like this. So when you draw a fourfold axis and you draw 4 of them, you see there is already a fourfold symmetry, so it by default generates a fourfold symmetry in the middle. So for my simple understanding, I am dividing this unit cell into 4 parts. Don't misunderstand these lines as some planes or some lines or whatever. I'm just dividing it into 4 parts for my easy understanding. So now, as I said, my molecule is some letter like F. So if I have a molecule F, which is located here, since it is body-centered lattice, I lattice, I should have another F like that in the center. But how? 1/4 half shifted along B, half shifted along A, and half shifted along C. That means it is somewhere here, which is then projected on the board. So when you do that, you write F with a plus half sign, which means this F is projected on the board, but actually it is halfway up the unit cell. It is halfway along B, halfway along A, and halfway along C. So now we try to apply the fourfold axis at these 2 objects. So when you do this 90-degree rotation, it goes there. When you try to do another 90-degree, I am trying to extend these 2, it appears there. You do another 90-degree, it comes here. Similarly, the translation component related objects are here, as I am quickly drawing. This is translated here. So what you get is just the translation related objects, but about that fourfold axis. Right? And now for this, remember this is already halfway up. So this also will have same thing, but always plus half. So if I try to number these points, 1, 2, 3, 4, 5, 6, 7, 8, what would be those equivalent points? Those equivalent points would be, if I can write it here, 1, x, y, z, 2 is y bar x, z, 3 is x bar, y bar, z, and 4 is y, x bar, z. Fifth one is x plus half, y plus half, z plus half, which is the body center atom. Then sixth one is half minus y, half plus z, sorry, half plus x, half plus z. Seventh one is half minus x, half minus y, half plus z. And eighth one is half plus y, half minus x, half plus z. So now can you tell me, somebody, if what is the relationship between 1 and 7? The relationship between 1 and 7 is nothing but a 2-1 screw located at 1/4 along B and 1/4 along A parallel to C. You get it? If I rotate that F by 90 degree and translate it half, these two objects are generated. This object, if I rotate by 90 degree and translate half, it comes here, which is halfway up. So these two are 2-1 related. Similarly, these two are 2-1 related. These two are 2-1 related. These two are 2-1 related. So what we have as 2 is related to 8 by 2-1. This object is nothing but this one translated there and translated here. So 3 and 5 are 2-1 related. This 4 is translated here. So 4 and 6 are 2-1 related. So 1 and 7, 2 and 8, 3 and 5, 4 and 6, these are related by 2-1 screw. Now let us try to draw 4-1 on this side in the same way. So when we draw 4-1, let's see that we should have the fourfold axis at the corners as usual, considering this as B direction and that as A direction. And it is not 4, it is 4-1. So the notation for 4-1 is anti-clockwise, opening like that. So the symbol is slightly different. Now for my understanding, I am just dividing it into 4 parts. So this is just the symmetry for 4, 1. Now what I want to do is I want to put the objects. If I put the object here, which is my object F, and the object which is here is F with a plus half. This was there at that other one also, I4. So now when I'm doing 4, 1, this is a 4-fold rotation and 1/4 translation. So the rotation will remain as it is. The translation we have to add as plus 1/4. Similarly, again rotate 90 degree and do 1/4 translation, so it becomes plus half. Then you rotate it again by 90 degree and translate 1/4, so it becomes plus 3/4. So these 4 objects are not on the same plane, but rather 1/4 up, 1/4 up, 1/4 up, and so on. So if we draw the translation related objects, it is not difficult to draw. Sorry, plus 3/4. Okay, I forgot to mention one thing here. See, between this point and that point, which is equivalent to 3, this point is equivalent to 3, there exists a 2-fold axis. And between 1 and 3 here, there exists a 2-fold axis. So at every midpoint of the edge, you have a 2-fold axis. And these are 2 1 screws. While I am doing 4, 1, you will see that these 2 1 and 2's interchange their place. So now if I do the same with this point, this is already halfway up, rotate and translate. So this goes 3/4 up. Then you rotate and translate. 3/4 plus 1/4 is 1, which means it goes to the next unit cell. So when it goes to the next unit cell, what we draw here is the object at the same level like that. And then we rotate it by 90 degree, it comes here with a translational component of 1/4. So I draw the translation related objects. At all the corners. What do we see now? Between these two F's, there is a 2-fold axis, because there is no translational component associated with F. Similarly, both of them are at same translational component plus 1/4, but related by a 2. Here also the same thing, and there also the same thing. This and that are 2-fold related, but at same level of 3/4. What is the relationship between this F and that F? From here to there, it is 180 degree rotated, half translated. So this point in this particular space group is a 2 1 screw. So now can you see the difference between these two? I4 and I41, the 4-fold axis are located at similar positions. Here it is 4 and there it is 4, 1. But the 2 1's here are at the 1/4 positions. Here at 1/4 positions you have 2. And in this case, you have twofold at the edges, whereas here at the edges, center of the edge, you have 2, 1. And I leave it to you to determine the equivalent points just like this. So you do it yourself and check with the textbook. I'm sure you will be able to identify the equivalent points for I41. Is there any other question that we can talk about? See, the problem that you are trying to address is sine beta, and I replace beta by 180 minus beta because sine beta is equal to sine 180 minus beta, and 180 minus beta is nothing but beta star. So sine beta and sine beta star are one and the same. So if there is no other question, maybe we can close the session. It is nearly 1 hour. So if you have any further doubt, please send email. You can directly mail to me, or you can post your query in the portal. So we will address that. Okay? Thank you.